My name is William Shipes, Professor Shipes, and I'm here to start your 108 class. Now, what we're going to do first is we're going to start with a review of stuff you should know coming into Math 108. Now, this is stuff you should have learned in middle school, high school, or in Math 104 if you took this here at USCA. It's a review, like I said, so if you don't know this information, you really need to take your own personal time and brush up on it, or even consider, if you haven't already, taking Math 104. The first thing that we're going to go over in our review are sets. If you haven't already, you should have already uploaded or should have already downloaded the corresponding notes that go with this video lecture. They should be in your Blackboard account under course content. It should just be called review. Now, I'll have a set of lecture notes to go with every lecture that I do and record this semester, so it should be available to you. And you should have a video right next to it under your course content as well. So, the first thing we're going to do is go over the type of sets. There's only two of them. You can have a finite set. That's a set where all the elements can actually be listed, or you can have an infinite set where you can't list all the elements inside the set. Now, you can also have an empty set. An empty set is actually an example of a finite set. An empty set has absolutely nothing in it. We represent that with a zero with a slash through it. It's not the same thing as a zero. You have a set with a zero in it. That set doesn't contain emptiness, it contains a zero. So it's different from the empty set. So make sure if you have to write something as an empty set, it's a zero with a slash through it and not just a zero. Alright, so now that we've got all that straight, I've got four sets written here. A, B, C, and D. Set A has a 1, a 3, and a 5. Set B has a 1, 2, 3, 4, and 5. C has a 5, 6, 7 onto infinity, so it keeps going up by 1 onto infinity. And set D is -1, -2, and -3. Now, a few things we need to know. A set can be a subset to another set. A set can be equal to another set, or a set can be disjoint to another set. So, set A is actually a subset of set B. Now, what makes it a subset? So, subset means that every element in A is also in B. So, this 1 is in B, this 3 is in B, and this 5 is in B. Therefore, A is a subset of B. Now, B is not necessarily a subset of A, because B also contains a 2 and a 4. A does not contain a 2 and a 4, so B is not a subset of A. Now, A is not equal to B. So we can actually do a little bit better. Instead of writing it just as a subset, we can actually write it as a proper subset. So your notation will look like that. A is a proper subset of B. Now, the next thing we see here is disjointness. Let's talk about disjointness for a minute. Now, disjoint means that no elements of one set are in another set. So if I'm trying to look at B and C, if I want B and C to be disjoint, they can't share any elements. Now, they share a 5. Because they share a 5, sets B and C are not disjoint. Now let's try to find a disjoint set. Let's look at A and D. A has a 1, a 3, and a 5. D has a -1, a -2, and a -3. They share no element in common. Therefore, we can say that A and D are disjoint. So A Now, the only other thing that we need to talk about with sets at the moment are sets that are equal. Now, equal sets are just what they sound like. So, sets that have the exact same thing in them. Now, it doesn't have to be in the same order, but they have the same thing. We don't have any examples of equal sets here. Obviously, A equals A, B equals B, C equals C. A set equals itself. But if I had another set here, let's call this set x. And it's equal to 5, 1, 3. Now, like I said, order doesn't matter. 5's in X, 5's in A, 1's in X, 1's in A, 3's in X, 3's in A. Therefore, set X is equal to set A. That's how equal sets work. Now, there are some common sets that you need to be familiar with and should already be familiar with. The natural numbers, integers, rational numbers, and irrational numbers. Now, natural numbers are just as natural as they sound. They start with 1 and they go to infinity, counting by 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You get the point. Integers also go by 1, but they go from negative infinity to positive infinity. So they start with the negatives. So you can start negative 3, negative 2, negative 1, 0, 1, 2, 3, on to positive infinity, and also goes back to negative infinity. Rational numbers are any number that can be written as a fraction, as long as the denominator is not 0. So P over Q, where P and Q are integers and Q is not equal to 0. So if you're looking at it, 1 is a rational number because 1 can be written as the fraction 1 over 1. 4 is also a rational number. 4 can be written as 4 over 1. Okay? 0.5 is a rational number. Can be written 5 over 10, also can be written a half. So if you're looking at it, any number that actually, or any decimal that terminates or repeats can be written as a fraction and is therefore a rational number. So if you're looking at, see, 0.333 repeating, obviously that's a third. That's a rational number. If you want to look at the approximation for pi, 22 over 7, obviously that's a fraction, so it's a rational number. If you want to think about, like I said, any integer you can think of, or any decimal that stops, so 0.53 is a rational number, because it can be written as 53 over 100. Okay? Irrational numbers. They can't be written as a fraction. They are also not terminating or repeating decimals. So any decimal that doesn't terminate and also doesn't repeat is an irrational number. So you take a number like pi. Pi is the most common irrational number that people normally think of. So that's 3.14, and then it goes on. It never repeats. It just keeps going and going and going. That would be an irrational number. Another one, square root of 2. Square root of 2 doesn't terminate, doesn't repeat, so square root of 2 is an irrational number. So those are some you should be familiar with. If you're not familiar with them, familiarize yourself with them. Make sure you know, because sometimes when we write sets up, what we'll say is the set of natural numbers between 4 and 22. Or the set of integers between negative 30 and positive 30. Or the set of rational numbers between 1 and 5. Set of irrational numbers between 1 and 22. You can write sets like that, so you need to be familiar with these definitions. Now, the next thing that I'm going to go over is inequalities and interval notation. So you should be able to go seamlessly from inequalities to interval notation and back. Sometimes in the questions that we ask you, we're going to want you to write it as an inequality. Sometimes we're going to want you to write it in interval notation. You should be able to go and do either. So if I want to go from this inequality to interval notation, something I need to note that x is greater than 8 is not equal to. Whenever it's just strictly greater or less than, I'm going to use a parentheses instead of a bracket. So x is greater than 8. So 8 is my lower bound. I've got a parentheses. And then that goes to infinity. That's your infinity sign. Now, if it is equal to, like it is in this instance, x is greater than or equal to 8, then I'm going to use a bracket. So 8 is my lower bound, goes up to infinity. You never put a bracket on infinity. You always put a parentheses. Now, if I want to go the other direction and go from interval notation to inequality, here I have between 4 and 12. I have a bracket, so it's equal to. That means that 4 is less than or equal to x is less than or equal to 12. Now here I have parentheses. So 3 is 6. That means x is between 3 and 6, but not equal to 3 or 6. So 3 is less than x is less than 6. And that's simply how you go between interval notation and inequalities, and vice versa. Here in Math 108, we're going to deal a lot in polynomials. There's going to be a lot of different polynomials we go through. Now, usually the first thing that I wind up doing is putting them in what we call standard form. Standard form is where we take the variable with the highest exponent and we put it first, followed by the variable with the next highest exponent, and then on down to the constant term. So let's go ahead and do that. Let's put this in standard form. So the variable with the highest exponent is right here, the 2x to the 4th. So I'll write it first, 2x to the 4th. Up next, the next biggest exponent I have is this 5x squared. Next, I have minus 8x. And then finally, I put my constant term, minus 3. Once you have it in this standard form, it's really easy to point out the other 3 questions that go with it. So, if I want to know what degree this polynomial is, that's simply asking me what is the biggest exponent on the variable in the equation. Now, sometimes there will be exponents on these individual numbers. We're not worried about them. We're worried typically only about the exponents on the variables. So here, the highest exponent on a variable is this 4th, so the degree of the polynomial is 4. What is the leading coefficient? The leading coefficient is the number in front of that variable with the highest exponent. So my leading coefficient here is 2. Now, lastly, it asks for the constant term. The constant term is the term that's going to stay constant no matter what the variable is. So obviously, it's the term without the variable. In that case, the only term without a variable here is this negative 3. Now, if you had more than one constant term, what you would need to do is combine and simplify that entire equation so you only have one constant term. And that is how you put the polynomial in standard form, find the degree, find the leading coefficient, and find the constant term. Now, as I said, we're going to have to do a lot of simplifying of polynomials, so let's practice that. So here I have 5sx minus 2y plus 7z to the 3rd plus, parentheses, 2y plus 5sx minus 4z to the 3rd in parentheses. Now, the first thing we can see is that these parentheses aren't really doing anything here, so we can just drop them off and rewrite the problem. Okay, now all we have to do is combine like terms. So, let's go about identifying our like terms. This and this are like terms because they have the same variables. This and this are also like terms. And lastly, this and this are also like terms. Now let's take it one by one. So 5sx plus 5sx. 5 plus 5 is 10. Now, we've completed the first step. Now, let's combine these like we said we were going to in this step. So, negative 2y plus 2y. 10sx, we're going to leave it alone. Negative 2 plus 2, that's a 0. So essentially, these two cancel out. Now, all I have to do is simplify this last term. So, 10sx, 7z to the 3rd minus 4z to the 3rd, that's just simply going to be 3z to the 3rd. And I can't combine these terms because they don't have the same variables. Therefore, I have simplified the polynomial as much as I can. Now, we're going to hit a few properties here and a few methods dealing with polynomials. So the first one that we need to review is the distributive property. So remember with the distributive property, you've got this x times this 3x plus y. Okay, this 3x plus y is obviously in parentheses. So we need to distribute this x to both of these terms. So I'm going to distribute this x to this 3x, and I'm also going to distribute this x to this y. So x times 3x plus x times y. All I have to do now is simplify. X times 3x is 3x squared, and x times y is simply xy. Distributive property. Now the distributive property leads right into the FOIL method. FOIL method just stands for first, outside, inside, last method. So if we simply follow the acronym, x times x would be our first, x times 4 would be our outside, 3 times x would be our inside, and 3 times 4 would be our last. So let's do that again. X times x plus x times 4 plus 3 times x plus 3 times 4. Now, all we have to do is simplify. X times x is x squared. X times 4 is 4x. 3 times x is 3x. And 3 times 4 is 12. Now, we've not simplified as far as we can go. We still have to combine our two like terms, which are 4x and 3x. If we do this, we get x squared. 4 plus 3 is 7, so we get 7x. And then plus 12. We have done the FOIL method and simplified. Now, on this side of the board, we're going to start dividing by monomials and review that. Now, x is the monomial we're dividing by in this case. It doesn't have to simply be an x. It could be a 3x, a 4x, a half x, a 0.75x. A monomial is simply a one-term thing. So it just means a one variable thing. Now, there's several ways you could go about doing this. You can do it all at once, but I'm going to break it down into steps. When I divide by a monomial, typically what I'm going to do is I'm going to separate it. So I'm going to say this is the same thing as 3x squared over x minus 4x over x. I'm going to distribute this x to this and to this, and then I'm going to simplify. So I've got two x's on top, one x on the bottom. That means this one x on the bottom is going to cancel one of these x's on top, so that I'm left with 3. 2 minus 1 is 1. So 3x to the first. Now x over x cancels as well, because anything over itself is just 1. So I wind up with 3x to the fourth, or 3x to the first minus 4. Now, I don't have to leave that 1 up there. If I want to simplify further, I can just call that 3x minus 4. That is divided by monomials. Now, if you wanted to, you could have done this a little simpler if you really get the hang of it. You just have to remember that you have to distribute this x to both. So you can say, okay, I know this x cancels one of these x's. That leaves me with a 3x. I know that this x cancels this x here. And simply go to your answer. If that works for you, that's fine. If it takes you a few more steps, that's fine. Alright, the last thing we're going to go over in this review is the coordinate system. We use the coordinate system a lot. A lot of times we'll use the TI 83 or 84, typically the 84 in this class, in order to graph things for us, but we also need to be able to do it by hand. So, just a quick review of the coordinate system. Our horizontal line here is our x-axis. Our vertical line here is our y-axis. The center here lies the origin. Now there's 4 quadrants. quadrant 1, 2, 3, and 4. Now, easiest way to remember that is quadrants go counterclockwise. Alright, so if I were going to graph a point, because if you can graph a point, you can graph 2 points and connect them and make a line. So let's just quickly review about how to graph a point. If I wanted to graph the point 2, 3, means I would go right 2 on my x-axis, up 3 on my y-axis. Plot my point there. That is the point 2, 3. Right 2, up 3. That's the coordinate system. That's the final thing that we'll review. After this, you should be able to access your Chapter 1 information. Hopefully everything in the review you know and are familiar with that we can build upon during this course.